This is the startup screen of the simulation software. On the right-hand side, you see the buttons for access to the tutorials and direct access to the database containing the storage systems, the PCMs and the PCM objects. On the left-hand side, you have the menu bar containing the Home button, the Setup button, the Calculation button, access to the database, importing comma-separated values, representing simulation results, and representing a small summary. Let's start with a simulation of a heat storage system. First, we choose the storage system. In this case, a storage system which was used in the university laboratory. With this information button, you can get access to PDF data holding the construction of these storage system. Then we choose our PCM, in this case ATS44, and according to the RAL quality mark, we see here the enthalpy distribution through the area of phase change. Now we choose the objects which should fulfill our storage system and holding the ATS44. In this experiment, I choose heat cell disks 180 mm diameter. Here the information button shows you the direct information of the producer for heat sticks and heat seal containing all important data for these kind of objects. After defining our storage system, we now can simulate our storage system either as a response test, constant thermal power, or a dynamic simulation. In this case, I will only simulate a response test. I initialize the tank system to 55 degrees Celsius and now define the supply temperature to the storage tank. The schedule can be fulfilled with steps in 1 second steps, and we start with 0 second, and for example for a floor heating system we will run with 30 degrees Celsius and 0.25 kilograms per second. Adding a next step could be after 1 minute. In my case, I want to investigate the storage system over 10 hours, that means 36,000 seconds. I will keep a constant supply temperature and a constant mass flow. With this button I can simulate this setup. The results show us the behavior of the heat storage system. At the beginning, when we bring in 30 degrees Celsius supply temperature, we get a return temperature of 55 degrees Celsius, which equals the initializing temperature. After approximately half an hour, the sensible heat is gone out of the system and we go down to the phase change temperature of the PCM, and then we have the heat exchange until 4 hours, and then the storage system is empty. If we calculate the power of the system, this would be done by multiplying the mass flow by the heat capacity by the temperature difference, which can be done with the power diagram. The blue line represents the delivered energy or power from the system. At the beginning, when we have a very high temperature difference, the system delivers up to, 26 kilowatt. After the sensible heat is gone, we go down to anywhere around 40 to 50 kilowatts and then go down to 0 until the storage system is empty. If we integrate power over time, we will get the energy which was delivered from the tank system, and we see that the system, that is the red line, delivers 45, close to 46 kilowatt hours in total. Now this is a simulation which shows the temperature distribution inside the tank and the behavior. We have 20 layers which deliver hot water in the upper layer, that is the 20th layer. If you see here, cold water is going into the system from bottom top down and top up, and the system delivers high temperature until 4 hours and then runs empty. Now this is not a realistic simulation. This is a simulation which is done in the laboratory to get an idea of how much energy is storable in the tank system and what kind of supply power can the tank deliver. If we want to simulate this storage system in a residential, non-residential building or industrial process, we have to do the simulation much more dynamically. Let's have a look to a normal residential building and simulate these storage system in a residential building under dynamic boundary conditions. You see here a normal residential building which is simulated with Energy Plus, and Energy Plus delivers the system loads for the heating system to provide enough energy to heat the building during day and nighttime. This is a winter time, anywhere outside temperatures between 3 degrees Celsius and 7 degrees Celsius, and the energy demand over the day varies anywhere between 2 kilowatts and 11 kilowatt. If I take out the energy demand, we see that we have approximately 3 kilowatt heating demand until 5:30, afterwards 7 kilowatts, then 2 kilowatts over daytime, then 11 kilowatts until nighttime, and then back to 2 kilowatts. So let's take over this schedule from the simulation, and I prepared these schedule here. You can export or import schedule data. Here is my example schedule for this building, and as already shown, we have an energy demand over daytime which varies between 3 kilowatt during nighttime and 11 kilowatt for these temperature difference or temperature distribution over daytime up to 11 kilowatts. I initialize the temperature I initialize the tank storage system with 30 degrees Celsius, which is, as you see here, too cold to deliver the supply temperature for the floor heating system. So when we start the simulation, the first step would be that the here programmed heat pump must regenerate the tank system and also delivers the energy for the building, which shouldn't be a real problem because the heat pump here is able to deliver 50 kilowatts. So let's simulate the whole day. You see here the temperature distribution in the system at several measuring points. As already mentioned, the storage system is empty at the beginning of daytime, and we see here that the source, the heat pump, is running and delivers supply temperatures to the heat storage system to be regenerated. The generation process ends at about 4:30, and the rest of the time until 13 o'clock we have the system running self-sufficient. Afterwards the system is the next time regenerated and then runs self-sufficient for the rest of the day. These are the storage temperature. Here you see what kind of temperatures the storage system delivers for the floor heating system, and this is done anywhere between 4 o'clock and 13 o'clock, and here in the nighttime after 20 o'clock. If you cumulate all the hours, you get a self-sufficient time over day up to 12 hours for a day. Here you see the stored and delivered energy from the system, which runs from the heat pump into the storage system and out of the storage system into the floor heating system. In addition, you can see the mass flow between the tank, the floor heating system, and the heat pump.